This tutorial will guide you through the design of this range of metric bolts. That's customizable. You can put in any metric bolts that you use regularly. The bolt length is customizable, as is the thread length, making it a very diverse bolt. And to go with that bolt, there is a simple nut that comes in all the range of sizes as well. Before we start, it is worth having your list of metric bolts that you use. The nominal diameter will come straight from the name. The pitch will be on a metric bolt chart, international standards. Search that, you'll find a column labelled P for pitch and S for spanner size. Once you've got that list sorted, we will indeed create a new metric standard part in Inventor and start a sketch on the XY plane. Here, the heart of this nut and bolt is the nominal diameter, which equals, we can just set that to 10 for now. We're going to set up some rules to drive the nominal diameter. And we'll also, under the Manage tab, Parameters, which is also accessible with the FX at the top ribbon, add in a text parameter for bolt name. Add in a numeric for bolt length, and a numeric for thread length, a numeric for just the pitch, and one for nominal spanner size. It's handy having that information available. The bolt length by default has 3 times the nominal diameter, and the thread length, 1 nominal diameter. Looks symmetrical and cute. With those 4 set up, you can have a look at the list of bolts that you want to include. Copy that list into, under bolt name, we'll right click, make it a multi-value list, paste our bolt names in, add. And now we've got the selection. At the moment, that's not driving anything. So we'll set up some rules. Once again, under Manage, add a rule, and we'll set a rule up for the nominal diameter. We'll just be using if-then statements. I have set these up already. If bolt name equals M5, then the nominal diameter will equal 5. Else if, and go through your list. Copy that into the nominal diameter, Control V, and comment out the title with an apostrophe. Save and run. Add another rule for pitch. Similarly, if-then statements to convert from bolt name to pitch. Comment out the title, save and run. And the last one we need is the nominal spanner size. If-then statements from your favorite isometric bolt chart, and paste. So with that bit of code set up, in our parameters, we should be able to see the nominal diameter changing automatically, the pitch and the nominal spanner size also changing based on the rules that we just set up. Let's get started. Start a sketch on the XY plane again. We're going to do the head going backwards, negative Z direction, and all the head information on that side of the XY plane, all the shaft on the front side. Starting with a 6-sided polygon, also known as a hexagon, create the spanner size, SS, which needs to be slightly smaller than the nominal spanner size so that the spanner actually fits on. And for 3D printing, I'm finding that 300 microns is enough. That's all we need for the head. We shall extrude that hexagon. We're going to take it backwards. A head height, label it HH. Considering the ratio of head height to nominal diameter based on the international standards, it averages out that the head height is around about 68% of the nominal diameter. We'll label this as we go. The spanner size, that's fine. The extrusion is the head height, and our initial sketch was nominal diameter. Now we'll put a chamfer on the bottom of this head by creating a circle that has a width of spanner size, diameter rather, of spanner size, and we'll do an extrude of that circle, take it backwards at an intersection of 55 degrees. And just chop off those corners. You can label that one the bottom chamfer, and we'll put a sketch on the back doing exactly the same. Diameter of spanner size, finish and extrude. The other direction, intersect at 55 degrees. Let's go home. Label that one top chamfer, and with the head set up we can save this as metric bolt save, and up to here it's the same for the nut, so we'll do a save as metric nut. So we have got a nut and a bolt. I'll work on the rest of the bolt and then come back and do the nut. The shaft, it's going to be sketched on the XY plane, and this shaft needs to be a little bit smaller than nominal diameter. We'll call it shaft and make it nominal diameter minus 0.2 of a millimeter, or 200 microns. For 3D printing, making the shaft 200 microns smaller and the clearance hole 200 microns bigger provides the perfect tolerance. We've got that base circle for the shaft drawn. At this point, turn off the visibility of the nominal diameter so that we don't extrude the wrong thing. Here the bolt length we've already set up. It's going to be extruded bolt length. I'm going to stick a little fillet of 5%, 0.05 of the nominal diameter, and a chamfer on the end of 10% of the nominal diameter. And now we'll just label this correctly as bolt length. So for the thread profile, we'll be following International Standard 68-1, where the thread profile is based on an equilateral triangle where all sides are equal to the pitch. Other measurements are taken from the height, which we're not given. We need to calculate the height of this equilateral triangle. Knowing that all sides are pitch, the base of the triangle will be half of pitch, p divided by 2, and we're looking for the height. Using Pythagoras, we'll label the triangle with the hypotenuse being C and A and B being our two shorter sides. We're looking for A, so we need to find the square root of C squared minus B squared. Substituting in, H will equal the square root of the pitch squared minus half of the pitch squared. Expand those brackets, P squared is P squared and 2 squared is 4. Now we've got a whole pitch minus a quarter of a pitch. A whole pitch is 4 quarters. 4 quarters minus 1 quarter will be 3 quarters of the pitch squared. We can simplify that a little bit. Square root of 3 is a third, and it will stay as the square root of 3. Square root of 4 is 2, and the square root of p squared is p. Pythagoras' rule will work if you want to type that straight in without rearranging, but it's just a little bit easier and neater and fun to do that simplification. Now we know how to set up the thread profile. We're going to start a new sketch for that thread profile. We want to be perpendicular to everything that we've done so far. So the YZ plane runs right through the middle. That's the one that we'll choose. And at the end here of our shaft, we'll set up a little thread that we can cut into the shaft with. What do we want? A rectangle. Turn construction lines on and build a rectangle that has a width of pitch and a height of, the thread height equals the square root of 3 divided by 2 times the pitch. Now our equilateral triangle is going to cut into the shaft, so we want it pointing down towards the shaft for this side. And the profile has us chopping off a bit of the top of the equilateral triangle. So we want to set up a line here and at the bottom, and dimension from strong to weak 1/8 of the thread height. or thread height divided by 8. And on the bottom, strong to weak, this is 2/8 or 1/4 of the thread height. And there's a little arc. That little arc can be chopped into the shaft, and for the internal thread there's a little arc at the top there. So to create that arc, we take a line perpendicular to the side of the triangle and take it into the middle, 60 degrees, wait for it to snap, and down to the other corner. Then, to make sure that locks how we want it, of course we're on the YZ plane. It looks vertical, but we're actually dealing horizontal here at the moment. We lock those 2 points. Turn off the construction lines and build an arc, center point arc. Select the line tool and just run around the rest of the thread profile. Before we finish that sketch, let's just align it with the shaft. So we'll project geometry, top edge of the shaft and the very front of the shaft. Then do a collinear constraint with the top of the thread profile and a collinear constraint front of the shaft with the front of that pitch. Finish that sketch and we'll coil around the Z-axis. We're using pitch and height method. The pitch is pitch and the height, call that thread length. Let's go home, label that coil thread profile. Coil can be thread. Turn on the nominal diameter visibility so we can see when we change the bolts, everything changes accordingly. The bolt length works and the thread length works. That's the bolt finished. Save that. Into the nut. For the nut, we don't need the bolt length parameter. We don't need the thread length parameter. And that's all we need. We do need a clearance hole. So let's start a sketch on the XY and create a circle with a width of clearance hole, which will be equal to the nominal diameter plus 200 microns. So the hole's a little bit bigger so that the shaft will fit through. Turn off the nominal diameter now and extrude backwards through all a cut for the clearance hole. That sketch is CH. We will suppress that feature so that what we actually want is a threaded hole, of course. We only need to put in a tap hole. There's tap hole on charts, but they relate to a drill size. For 3D printing, we need to know the exact tap hole. So we need to work out how far the thread is actually cutting in. So of the equilateral triangle, we know we've found the height, and that is 8/8. 1/8 of the top is chopped off, and 1/4 or 2/8 of the bottom of that equilateral triangle is chopped off. So we're left with a thread height of 5/8 of the thread height. What? Oh, 5/8 of the height of the equilateral triangle, yeah. The thread will cut in from the tap hole. It needs to get exactly to the clearance hole, and it's going in a distance of 5/8 of the thread height. And it happens at the top and the bottom. So the diameter will involve the clearance hole minus 2 lots of 5/8 of the height of that equilateral triangle. We have not set up the thread height. If we had thread height set up, we could type in that formula. Obviously we would make it 10/8 and then 5/4. But we haven't got the thread height set up in this file yet. And it's not every day you get to work with thirds. Now, it's common knowledge that the thread height is √3 on 2 times the pitch. So we can simplify this only a little bit. Multiplying by 2 and dividing by 2 cancels out, leaving a tap hole of clearance hole minus 5√3 on 8 times the pitch. Let's chuck that in. We'll start a new sketch on the XY plane. This one's going to be for the tap hole. And we just calculated it is equal to clearance hole minus 5 times the square root of 3 divided by 2 times the pitch. It's not divided by 2 though, is it? It's divided by 8. There we go. And that looks very nice. Finish that sketch. At this point we can suppress the clearance hole, and the tap hole can now be extruded backwards through all as a cut. Done. Label it tap hole. And do put a chamfer on the front and the back, especially for 3D printing. It makes it much easier to get the thread started and to clean up the thread. We do want that chamfer to be 10% of the nominal diameter. Start a new sketch on the YZ plane. That'll be perpendicular to what we've done. F7 to chop that in half. And here we're going to set up with construction lines on a little rectangle that has a width of pitch and a height of thread height equals the square root of 3 divided by 2 times the pitch. This equilateral triangle needs to cut into the nut pointing upwards. We're going to chop off 1/8 of the top, and we'll chop off the bottom. So we'll add those dimensions: strong to weak, thread height divided by 8, and strong to weak, thread height divided by 4. Similar with the arc on the other thread profile. This one's going to go at the top though. Perpendicular to the side of the triangle. Lock on over there. And again a horizontal, which looks vertical, constraint between those two. Turn off the construction lines. Start an arc from that center point there. Use some hard lines to mark in the rest of our profile. Before we finish, just line it up. Project geometry, top line, front line. Then we can do a collinear constraint. This needs to chop in, so the lowest part of the thread will be there. And finish that sketch. We can coil that profile along the Z-axis. Pitch and height method using pitch for the pitch, and just head height plus 2 pitches, so it definitely cuts all the way through. Turn the nominal diameter visibility on. We can see that our nut now adjusts with the ISO standards pitch, and we tested the bolt before. Control S to save, and we're done.